Hi everyone, welcome back. So this time we're going to be doing an expansion fan problem. So expansion fans are like reverse shock waves in the fact that they do everything backwards. So a shock wave compresses, an expansion fan obviously expands. A shock wave causes pressure to increase, expansion fan causes it to decrease. And so what we have right here is we have an expansion fan, we have a deflection angle, so that's this angle right here, where theta is equal to 23.38 degrees. Okay, there we go, got it. And we have our forward Mach line, because remember these are fans, they're not just one straight line, it's more like a little V. And I can get two angles from this. There is mu1 right there, the angle between my original direction and that Mach line. And then I have mu2, which is a Pokemon, and also the angle between the Mach wave and my flow direction afterwards. So we know that our Mach 1 is going to be equal to 2. We have a pressure that's equal to 0.5 atmospheres, and a temperature of 400 Rankine. And what do we want to find? We're going to find pretty much everything. Why? Because that's what the problem does, and I'm going to do it with you. I'm not leaving you alone. Okay, so we're going to find M2, P2, T2, P02, density 2, and T02, because let's literally get everything. Whoa, that's a lot of stuff. How are we going to do it? Very slowly, very carefully, one step at a time. Are we going to need the tables? Yes, we're going to need the tables for this, okay? We're going to need those tables. Otherwise, we're going to have some trouble there. Now, just like with our oblique shock, our normal shock problems, we're going to have to go to the tables because it's way easier than trying to solve any of those crazy equations. So in this case, for expansion fans, we're going to be going to a different table than we've been using the last few times. We're going to be going to Appendix C. Okay, so Appendix C, that's what we're going to need. And so now with the power of moving magic, I'm going to take you to Appendix C. Now, here I am at McGraw-Hill Connect, so I click on my ebook, and I'm going to hit the little bar on the side. I'm going to scroll down all the way until I find Appendix B. See, it's already open because I use a lot, but I want to go to Prandtl Meyer functions and Mach angles because I need Appendix C here. Okay, now what we're doing is when we're using our Mach number that we know at the beginning to find our Prandtl Meyer function, and then we're going to use what we know, our deflection angle plus Prandtl Meyer function to find our second Mach number. We're kind of going to go forward and back pretty quickly here. Our Mach number initially was 2, so I need to go down here. And there it is. Remember that this is multiplied by a factor of 10. So I'm going to go ahead and screenshot this so that I can underline all the information that I'm going to need. So right here, I need this guy. And I see my Prandtl Meyer function is going to be very careful about that, 26.38 degrees. This second column is what I need. And this one right here, this was for my Mach angle if I needed that. Not sure we'll need that in this problem. I don't believe we will. So for this problem, not going to need that. But otherwise, here are the details from our Prandtl Meyer function. Okay. With that, I'm just going to jump straight back to here. And so what we found then is that M1 is equal to 2, and therefore V1 is equal to 26.38 degrees. Now, V2 is simply equal to V1 plus my deflection angle. Now, I know my deflection angle. How do I know it? Because that was given in the problem statement. So that makes it pretty easy on us. So we have to do a little bit of addition. If you're struggling with addition like me, use a calculator. And luckily for me, I've got the solution right here next to me, and so I'm going to just pretend like I can do math in my head really quickly. I am decent at it, so long as I'm not giving somebody a tip at a restaurant. Then I do terrible. My wife has to check me every single time. I think I've already mentioned that like a billion times though. Okay, so now I have a second Prandtl Meyer function. I'm going to do the reverse of what I did earlier. I'm going to use V2, which is 49.76 degrees. And I'm going to go and find what my M2 is going to be from this. Now, because this is an expansion fan, I'm actually going to accelerate. It's going to be a higher Mach number than before. Okay, so I'm going to go ahead and X out this. Got that, looks good. I'm going to scroll down until I find something pretty close to that. And oh my goodness, it's beautiful, it's perfect. We actually have a line that's right matching it. And why do we have that? Because your textbook doesn't like to do math either. They didn't have to interpolate. They're not against making you interpolate, but this time we didn't have to. So right here is 49.76 exactly, which means we can have a Mach number of 3 afterwards. Happy days, we have it. A Mach number of 3, 49.76. So with that, we have our Mach number after the shock. Okay, let's write that down. 3.0, we got it. Good. Looking wonderful. Okay, now what we're going to have to do is start finding properties. That was not what I'm going to do. I'm going to click and drag. There we are. Because after my expansion fan, I'm going to define P01 and T01 and all that good stuff. And so when you see total temperature or total pressure, think the isentropic flow tables. Okay, that's the stuff where you want to go and get that stuff. That's usually where you're going to go when you see the P and not. Total pressure, stagnation pressure, you're going to go to Appendix A for your isentropic flow tables. And so what we're going to do now, we're going to go there. And we're going to get information both before and after the shock. So M1 is equal to 2, M2 is equal to 3. And then from that, I can figure out all the rest of my information. So I'm going to get P01 over P1. I'm going to get P02 over P2. I'm also going to get T01 over T1 and T02 over T2. Yep. I did not give myself nearly enough space there. I'm going to go ahead and erase that because I can't see anything. There we go. Move it over a little bit. That's looking good. Okay, now let's go to those tables and get all those values. Now I'm going to show you the values and I'm going to come back and we'll give from there. So, back to my handy dandy textbook. Don't need this guy anymore. I go over to the contents, I scroll down, and Appendix A is where I need to go this time. And I find my Mach number. Once again, be careful because at first it was power of -1, now it's power of 0. I need to go all the way to a power of 1 so I can have it be 2. I'm going to try to get all the values in the same slide. I'm not sure I can do it. Let's see, can I do it? I can. Happy days. So I'll go ahead and screenshot this. Now the one thing that's bad about a digital textbook is you can't see what the column headers are. However, I'm going to help you with that, so don't worry about it too much. Okay, so first off, here's our 2, and way down here, barely fit, here is our 3. Okay, so the first column is your pressure not P01 over P1 column. So I need this value. I'm also going to need this value right there. After that, I need to go to my T0 column, which is over here. This is the T01 over T1 column. So I need this value. I'm also going to need this value right here. Now, because I have an excellent memory and because I'm also just following along, so I don't have to worry about writing all this down, let's go ahead and jump back and write down those numbers. But just remember, if you don't see it here, you can look up at the top to see what the headers are. And we're just matching it to our Mach numbers. Okay, that's all we're doing here, matching it to our Mach numbers. Okay, back to it. Let's get those values written down. So I've got 7.824. I have 1.8, 2.8, and finally 36.73. Okay, we got that stuff right there. We're making our way. And so now, we have some little details that can help us out. First off, because this is an expansion fan, we know two things. One, we know that our total pressure stays constant. And two, we know that our total temperature stays constant. This one was true for shock waves as well, so you're probably familiar with that one. And now using this, I can go ahead and start calculating out my pressures. So first off, let's do P2. So P2 is going to be equal to, wait a second, how are we going to get this? We don't know what P02 is. We do, remember? It's the same one here. So we do that kind of like, chain rule thing. So let me see here. We have, let's start with P1. Okay, we know that. And if we multiply that by P01 over P1, well, that's now just P01. And we know that P01 is the same as P02. So if I multiply that by P2 over P02, these two are the same. That cancels, I'm left with P2. That looks right, I like it. I can do the exact same thing for T2, so I'm gonna go ahead and write it out, and then I'll do both of them at the same time. So it'll be T1 right here, I have T01 over T1, and then I have T2 over T02. Be very careful with the order there, so you don't mess any of this up. Now I'm gonna plug in my numbers. So I had pressure 1 was equal to 0.5, P01 over P1 was 7.824, and P2 over P02 was 1 over 36.73. And T2 is going to be equal to, let's get it, there we go, T1, which was, scrolling back here, I don't remember what it was, 400 Rankine, okay, that looks good to me. 400 Rankine, and we're going to multiply that by T01 over T1, which is 1.8, and then 1 over 2.8. Notice the over 1 because I flipped this. It's not the same as I had right here. I had to flip it. That's why it's divided by 1. Not flare it, flip it. Okay, now let's go ahead and plug this in a calculator and see what we get. Okay, now for the pressure, what I get is that it is 0.106 atmospheres. It went down in pressure, which makes sense because I'm being expanded. It should go down in pressure. And now let's figure out what the temperature would be. And for the temperature, I get 257 degrees Rankine. It got colder because, once again, it's being expanded. That makes sense. We're doing good here. We're doing good. Now what we're going to do is we're going to go ahead and start calculating our total pressure and our total temperature, because we haven't done that. And we can let's go ahead and calculate density as well. We'll do density first. So density 2 is going to be equal to P2 over RT2. Because remember, this is an ideal gas relation. We're using air. We can do that. It works out pretty nicely. If you're wondering where this came from, you might know this equation looking like this. PV equals RT. That specific volume is the inverse of density. So I can also have that P is equal to density RT. Just making sure you know where it comes from. Okay. So I plug that in here. Let's see what I got. I have my pressure of 0.106 atmospheres. That looks good. I got my ideal gas constant of 1716 foot-pound force per slug degrees Rankine. And I have a temperature of 257 degrees Rankine. And what you might be noticing is that that is atmospheres and this is not atmospheres. I'm going to go ahead and give you a handy dandy conversion, which is just 2,116. Okay, you can work out the math if you want to, but you can just trust me and know that it's 2,116. That will get us into slugs per foot cubed, which is what we want for our density. And let's plug that in our calculators now and see what we get. And what I get from that is I have 5.086 times 10 to the negative fourth slugs per foot cubed. I hate English units, but slug is still a fun name. Okay. Last two things we want to calculate for this problem are P02 and T02 because it's the last two things asked for. So these are both pretty easy. So P02 is going to be equal to my ratios I already have here, which is, yes. So I know what P01 over P1 is, and I know that P01 is the same as P02, and so I can use that to help myself out here. So this is the same as calculating P02. Like, I'm calculating P01, yes, but they're the same total pressure. It doesn't change the expansion fan, so just calculate the one that's easiest. So I plugged it into my calculator, and what do I have here? I've got 7.824 times 0.5, and I'm going to do some math in my head here, people. It's dangerous territory, but I believe that's 3.912 atmospheres. Okay, that's my total pressure. And now let's figure out T02. Remember, it's equal to T01. I would find that by saying, okay, it's T01 over T1 times T1. We've done this whole chain rule thing a whole bunch, so hopefully you're getting really used to it by now. So that's 1.8 times my temperature, which was initially 400 degrees Rankine. And let's see here. You know what? I'm not going to try to do the math in my head. I'm going to plug it in a calculator. I can do this. It's fine. Calculators are fine. I get that it's equal to 720, which was definitely what I was about to tell you off the top of my head. Okay, with that, we have calculated the total temperature, pressure, density, pressure, temperature, and Mach number after this expansion fan. Woo, we did a whole lot here, people. Went to appendices quite a bit. Hopefully this helps you. The hardest part is probably when you're at the Prandtl Meyer functions. Everything else is pretty similar to what we've done with oblique shocks. So, hope this helps you. I'll see you all next time. Have an absolutely wonderful day. Bye-bye.